In Module 4, we are going to be studying the first law for open systems, and we start part 1 with defining what open systems are and understanding how we can solve problems using open systems. So far we've only looked at systems that were closed, and in the previous modules, we looked at piston cylinder devices and they were usually closed. Now we're going to switch to open systems and try and understand and apply the first law to these open systems. So an open system is also called a control volume system. So it's also called a control volume system. And what a control volume system means is, so we can write control volume as CV in this class as well. So CV is going to be referred to as control volume. And what this means is that an open system, essentially, mass crosses the boundary of the system. So up until now, we've looked at systems such as a piston cylinder device, and this piston cylinder device sort of had some fluid locked into it, and no mass was able to cross the boundary of the system if the boundary of the system was defined as, let's say, something shown in green right here. So this would be the boundary of our system, and no mass would cross this boundary. Now, heat and work could cross the boundary. We could create work going up, or we could have some heat coming in. Okay, but we couldn't have mass crossing the system. And now what we're going to do is we're going to study systems where we have mass crossing the boundary. So what do we mean by mass crossing the boundary? So an example of this would be filling up a tank. So if we fill a tank up, let's say we have a tank of water, we could have a faucet or something like that adding water to a tank. And if our control system and our control volume looks something like this, we now have some mass entering the system and increasing the level of this water. So that would be an example of an open system. Another type of open system that is often worked on a lot in thermodynamics is a water heater. So you'd have cold water coming in, and you would have a water heater, and you would have hot water coming out. So you'd have cold water coming in, hot water coming out of the system, and in the middle you would have a water heater. And the water would flow around this water heater. Now, we define our boundary here as shown below, and you can clearly see that there's some mass crossing the boundary here and some mass exiting the boundary through the exit where the hot water comes out. Another simple example of another open system would be, and probably the simplest open system, is just flow through a pipe, which we've looked at before. A flow through a pipe just has a control volume, okay, CV, like right here, a control volume, and as air or water or any other fluid flows through it, there's mass coming into the control volume. So we have some mass flow rate into the control volume and some mass flow rate out of the control volume. Okay, so the difference between a closed system and an open system is now mass is allowed to cross this boundary. And what we can say is that in an open system, we can summarize it as mass, heat, and work can cross the boundary. So all three can now cross the boundary. And what this means is that mass is no longer constant. So in some cases, the mass in the system will be constant, but in other cases, the mass might be different. Okay, the mass might be changing, just as when we fill a tank. So we can write an equation for conservation of mass that says that the mass into the system minus the mass out of the system is equal to the change in mass in the control volume. Okay, so if we start with a tank with 1 liter of water, and we start with that point, and then we add 10 liters of water, and we don't take any water out, that means that the change in the mass of control volume is 10 kilograms, for example. Okay, if 1 liter is equal to 1 kilogram. So we can write the long version of this equation, we can write it as the total mass coming into a system, so into the system during a change in time, delta T, okay, that's a change in time, minus the total mass leaving would be equal to the net change of mass within the control volume, or CV. Okay, and we can rewrite this in rate form. So we can rewrite this in rate form. So m dot is defined as mass flow rate, and what mass flow rate is just dm over dt, or the change in mass, delta mass, over the change in time. Okay, whichever version you have to use. And so we can say that the sum of the masses in, of the mass flow rates in, minus the sum of the mass flow rates out is equal to the change in mass in the control volume with respect to time. Okay, d dt times mcv. And obviously you can integrate all the terms if you want to find actual mass change over a given period of time. Okay, but we'll look at how we can do that. Now, in this module, we're going to study 2 different cases. And the 2 different cases are steady flow and transient flow. So let's take an example and understand if something has a steady flow or a transient flow. So an example of a steady flow would be pipe flow. So pipe flow in thermodynamics can be thought of as a steady flow, because we essentially have we can say that the total mass inside the pipe does not change with time. So if we have flow through a pipe, okay, we have a pipe, and our flow through the pipe goes through a control volume that we define, we can essentially say that if the flow is constant, if the mass flow rate in is constant and the mass flow rate out is constant, then it means that the mass inside this control volume is always the same. Okay, so particles of mass and pieces of mass are going to be moving along, but the mass is always going to be the same. Okay? That's very important to understand. It means that we can say that the mass control volume is equal to a constant. Even if the pieces of matter that are moving through are changing, if we do the sum of the mass at any point in time, the mass control volume is constant. Okay? And what that means is that if it is a constant, it means that dm over for the control volume over dt is equal to 0. So we can say that for steady flow, we can say that dmcv over dt is equal to 0. So now let's try and understand what's happening. So we can redraw this diagram and look at it from a volume flow rate point of view and using velocity to solve for the problem. So we can say that we have this pipe, okay, and through this pipe, we're going to say that we have a little piece here that's going to be called a differential volume. So we have dV, which is a little slice of the volume. Okay, I'll just write differential volume so that we have it. So it's a little slice of the volume through the system. Now, and we also know that there's a velocity in to our system shown by the symbol for velocity, which is v with a bar through it. Okay, and we also know that the system has a cross-sectional area A. Okay, so let's try and develop an equation for the differential volume flow. What is the differential volume flow in this system? So essentially, what is the volume flow for this little piece of differential volume that we have? And differential volume flow is just a volume flow rate. And volume flow rate can be written as V dot is equal to dV over dt. Okay, so differential volume flow rate would just be equal to dV over dt is equal to velocity multiplied by the area. So if we know the velocity and we know that the differential volume passes through an area, it gives us our differential volume flow rate. And we can write this also as dV dot is equal to VA times dt if we want to. So that's for our volume essentially passing through our system. Now, the differential mass going across this surface, or the differential mass now, is just the volume flow rate multiplied by the density. So we can say that dm, the differential of mass, is equal to the density times velocity times area times dt. Okay, and if we bring the dt over to this side, we can say that dm over dt is equal to m dot, which is equal to rho a v. And I just switched the a and the v just for convention purposes because we usually always write it this way. Now that we have this system, we can say that mass flow rate in our systems and in pipe flow or any flow that is simple with 1D flow, we can say that mass flow rate is equal to rho AV. It's a governing equation that we can use. So rho AV. Now, in thermodynamics, we don't really like using density too much. We like using specific volume. So we know that density is equal to 1 over specific volume. So we can say that the mass flow rate can be written as area times velocity over specific volume as well. Okay, just by the definition of what specific volume is. So we can interchange both equations depending on if we're given density or if we're trying to find specific volume from our tables, for example. Now, in this equation, just to keep it general, V is the average velocity. So sometimes velocity, and in most cases, velocity through a pipe is sometimes not always uniform throughout. So you might have flow that is faster through the middle of the pipe. So if I draw a pipe here like this, and I show you a velocity profile of the flow, sometimes the velocity profile looks like this. So you could have a case where the velocity is not uniform. So in this equation above, you have to use V average or V of the average. So you need to find the average velocity, which would be somewhere around here. Now, in most cases in thermodynamic problems, the velocity given is already the average velocity, or it just assumes that the velocity profile looks something like this. It just assumes that the velocity is the same throughout the cross-sectional area, essentially. Okay, so just a little bit of some information on area itself. Now, moving along from this, let's talk about flow, work, and energy of a flowing fluid. So we had said previously that for a closed system, in the previous module, we said that work energy, or we can say work or heat energy, can be transferred to and from the system. Okay, so in a piston cylinder device, for example, we can have flow of work going out of the system, which means our piston would move up, and we can have heat into the system if we're heating it up. Or we can have it cooling down, in which case the heat would come out of the system. Okay? Now, for an open system, we have mass crossing the boundary. So for an open system, we also have mass crossing the boundary. And in order to have mass cross a boundary, we actually need some work to do that. So we can say that some work is required to push mass into the system. So in order to move mass from one place to another, we need to do some work. And that work is usually created by either a change in pressure or by putting a force on a certain system that we have. And so we're going to draw a little system that explains how this could work. So as I'm drawing this, you can draw the system as well. So the system is going to look something like this, where we have one exit and one entry to the system. And this entrance to the system is going to be bound by this control volume. So we're going to call this our control volume. So our control volume is going to be stuck to the surface of the system. And the system is going to have some flow coming in through here and coming out through there. And this work that's required to push the mass into the system is called flow work. So let's look at what this means. So let's imagine that we have a block of air, okay, and this could be air or it could be any fluid. So this is going to be air for our example. And this block of air needs to be pushed into our system. And in order to be fully pushed into our system, we need to push it a certain distance L. And what we're going to do with this air is we're going to push it with an imaginary piston cylinder device, or not piston cylinder device, but an imaginary piston. So we're going to use a piston to push this air in, and we're going to apply a force on that piston. Okay, so this is just an illustration of how we could get some air into our system, hypothetically, let's say. And we also know that this system has a cross-sectional area A. Okay, so there's a force pushing this area, pushing this air through an area A and through a length L. Now, at the same time, on the other side of the system, we have another block of air that is here and that is ready to be pushed out. And this block of air is going to push an imaginary piston that is waiting to be pushed through the same area A. Okay, it has the same area A, and with the air on the left coming in, we're actually going to push the air on the right coming out, or this block of air essentially. Okay, and the piston, what's going to happen is it's going to move in this direction. Okay, again, this is an illustration and we're using an imaginary piston to try and illustrate our point. Okay, we can also say that the block of air, okay, our block of air has a density, rho, and it has a mass, m, and we can say that there's a pressure P applied to this air. Okay, so let's write down a little bit of a narrative for this system. So we have this system, and we can say that if the fluid pressure, so if the air pressure is P, okay, we defined it as P above, and the cross-sectional area is A, then we can say that from our laws of pressure, we can say that force is equal to pressure times the area. So the force to push our block of air would have to be equal to the pressure times the area in which the force is applied. And we can go further than this and say to push the entire element, so the entire air element, into our system, we see that the force has to act along a length L. If the force acts all the way along the length L, then we know that we have our air is going to go into our system. Okay, and we can call this length L or distance L. And we can therefore say that F times L is equal to PAL, and we know that force times length is also equal to force times distance, which we should know is equal to work. So this term that we define as flow work says that the work to get some air into our system, some amount of air into our system, is equal to the force times the distance to push this air through, which is equal to force times the length, which is equal to PA times the length. Now, A times length is also equal to volume. So this is equal, the work is equal to pressure times the volume of that block of air. And so we can define this as the flow work. We can use any equation to figure out the flow work. But essentially, what this flow work is the other energy that goes across the boundary associated with the mass. So this is the energy that crosses the boundary associated with mass. So before we only had heat and work boundary. Now we have heat, work boundary, and flow work associated with how much mass is going across the boundary. So we can write that the total energy associated with the flow of mass is equal to the following. So we're going to call this energy theta because it's the total energy it's the energy of mass per unit mass. So theta is the energy from the mass divided by mass. Okay, so it's the energy divided by the amount of mass. And so this is equal to little e plus PV. So it's the energy of our whole system per unit mass. So this could have been written as follows. It could have been written as E per mass plus PV divided by mass, and can be rewritten as little e plus P specific V. Okay, so we're using specific energy and specific volume, as well as specific energy associated with only mass. So now that we have the energy for mass, we can recognize that this is equal to U plus V squared over 2, which is our kinetic energy. So we have internal energy plus kinetic energy, okay, per unit mass again, plus Gz, which is our potential energy. Okay, and then we have a term that's added to it that is called PV. Now, if you remember, we had defined our H to be equal to U plus PV in the previous module. So now, if we combine U and PV, we can actually use H in this equation. And this is where we essentially, why we use H and why H is usually used, because it takes into account the energy from the mass going through the boundary. So the total energy with flow of mass now takes into account the boundary through our term H. So we can say that for a system where the mass crosses the boundary, we can say that theta is equal to H plus V squared over 2 plus Gz, and this is essentially the total energy per unit mass. Okay, and the enthalpy term takes care of the flow work. So the enthalpy term, H, takes care of flow work. So this is very important. And we can write that the total energy of a flowing fluid of mass m, so if we write the total energy of a flowing fluid of mass m is equal to E mass is equal to mass times theta, which is equal to mass times H plus 1/2 V squared plus Gz. And we can also write this in the rate form, which would be E dot of mass. So this is the rate form, so it means that it's divided by the change in time, would be equal to mass flow rate times theta, which is equal to mass flow rate times H plus 1/2 V squared plus Gz. Okay, and now from this equation, we can now apply the first law for a control volume. So we can now apply the first law for CV. And for a control volume, we're actually going to apply the first law most of the time in rate form. So in the form with energy dot. The reason why is because we're interested in what happens through time, okay? We're interested in what happens in rate form, not necessarily in absolute form. But we can use both ways, but it'll be used more often in this way. So we can write that, so we're going to use rate form. So we can write that we remember that dE of the system, or the change in energy of the system, was equal to, and let me write it in non-rate form first. So the change in energy of the system was equal to E in minus E out. And beforehand, our E in minus E out was just equal to Q in minus work out. But now we have an energy associated with our system that is caused by the mass coming into our system and the mass coming out of our system. So we have to take that into account. Now, in this case, we're going to use the rate form. So the rate form is dE system divided by dt is equal to E dot in, so the rate of energy, which is the power, minus E dot out. Okay, so that means that we can write dE of control volume dt is equal to whatever is coming into our system minus whatever is coming out of our system. So what is coming into our system? So into our system, we always assume that Q is into our system. If we get a negative, we know that it's out of our system. So plus, now we're going to have to take into account the energy associated with the mass coming in. And this energy is the sum of m dot I, m dot in, times hi plus vi over 2 plus gzi. And the reason we have this summation is if we have more than one inlet in our system. So in a simple system, we have one inlet, in which case we just have one term, but we could have the sum of all the masses of all the different entrances to our system. So we could have two entrances and one exit, for example. So this is our energy flow rate in. Our energy flow rate out is W dot out plus the sum of M dot E, which is our exit. Okay, we're going to use an E for exit, times HE plus V squared E over 2 plus GZE, and that would be our energy rate out of the system. Now, the rate form of energy, so the rate form of energy is energy per second, okay, or kilojoules per second. The unit that we use the most in this class is kilojoules per second or joules per second. And this can also be written as kilowatts. And it can be also called power. Okay, so kilowatts is usually called power in other terms as well. So we'll look at how we can use power. So if you are asked to determine the power of a system, the power of a system is usually associated with W out. Okay, so you're trying to find W dot out, which would be your power. Okay, so moving forward from this. In this class, we said we're going to look at the steady state process, which is a steady flow process, and an unsteady flow process, which is our transient process. So we're going to start by looking at the steady state process, or the steady flow process. And the particularity of our steady flow process is it's used in many systems that we have in thermodynamics. So it's used in turbines, it's used in compressors, it's used in pumps and heat exchangers as well. And what that means is that once the systems are on and running, the turbine is going to get a steady flow of air or water going through it. It's not going to change, which means that a steady flow process means that we have energy overall does not change with time within the system. And that means that dE of control volume dt is equal to 0. Okay, the energy within our control volume is not going to change, and the mass with time in our control volume is also not going to change. So we can simplify our problem a lot. In a transient problem, we have a change in mass. Okay, in this case, we don't. And so it simplifies our system a lot. So if we look at the continuity equation, which is our conservation of mass equation, we can now go back to it and say that the sum of the mass flow rates in, which we had written at the start of this video lecture, is minus the sum of the mass flow rates out is equal to dt of mcv. But we know that this is equal to 0. So we're left with the sum of the mass flow rates in is equal to the sum of the mass flow rates out. And it makes sense, right? If we have a pipe with water flowing at 2 kilograms per second, the water is still going to be flowing at 2 kilograms per second at the exit. It's the only way, right? We have to conserve our mass throughout. So the sum of the masses in is equal to the sum of the mass flow rates out. And we can simplify our first law as well to say that we now have the left term, which is dE system over dt, is now equal to 0, which is equal to q dot plus the sum of the mass flow rates in times hi plus vi squared plus gzi minus work dot plus the sum of the mass flow rate exiting times he plus ve squared divided by 2 plus gze. And remember that the first term also has vi squared divided by 2. I added it later on. So we can now rewrite this equation in sort of the same format as we had it in our first law for closed systems. So for our first law for open steady systems, okay, so it's first law for open steady state systems, we can bring our Q and W to one side and our masses to the other. So what we're going to do is we're going to move our mass terms to the other side and we're going to keep Q minus W on the right. So we're going to have that m dot all multiplied by he plus ve squared over 2 plus gze minus hi plus vi squared over 2 plus gze ZE is equal to Q dot minus W dot, okay? Or we can flip it and say Q dot minus W dot. So that would be Q dot in minus W dot out, okay, the same convention as before, is equal to M dot times HE. And we can go even further than this, and I'm actually going to write on the left side too, because I like to have Q dot in minus work dot out on the left. So I'm going to say Q dot in minus work dot out. Okay, it's just exactly the same thing. I just like to have it on the left side. And we can now say that what if we bring our mass flow rate to the left side? If we bring our mass flow rate to the left side, we can use specific heat energy and specific work. Okay, so we remember that Q is equal to Q over M, which is also equal to Q dot over M dot. And specific work is equal to work over M, which is also equal to work dot over M dot. Okay, so we can write, if we bring the mass to the left side, we can write that Q minus W is equal to HE plus VE squared plus GZE minus HI plus VI squared over 2, both velocities over 2, plus GZI, all in brackets, and we would have this equation in our specific form. So we have two forms of the equation. We have one form that says that Q dot in minus workout is equal to M dot times this, but we can also use this other equation, which is using the specific form. Now, in this general equation, as you can see, I didn't put the sums. So I took the sums out just to make it a little bit shorter. Now, if you have multiple exits, you just have to add all the exits together. If you have multiple inlets, you have to add all the inlets together. Okay, so you do have to keep into account that if you have more than one entrance and exit, you'll have to take that into account with summing all the exits and summing all the entrances. But the nice thing about this is that we have two different equations. In most cases, you're going to use this first equation. So in most cases, we're going to be using this first equation. In some other cases, you will be using the second equation in case you're not given mass flow rate and you're just asked to find the specific values for, or you're given specific values and need to find velocity or anything like that. Now, there's a third form of the equation that you can use as well, which is the following. So we can just rewrite the second equation. We can just rewrite it as Q minus W is equal to HE minus HI plus VE squared minus VI squared all over 2 plus GZE minus ZI. So just combining the enthalpy terms, combining the velocity terms, and combining the elevation terms. Okay, so we can use either of those three equations, and sometimes it'll be better to use one over the other, but they essentially mean the same thing, and you can always derive all of them from the first equation. So that's why I like to start with the first equation, the one shown right here, because this one, you can always go to the other forms after. So this concludes part 1 of Module 4. And in part 2 of Module 4, we're going to start looking at some example problems and how we can solve problems using this first law for open systems.